chapter 5, we're going to get into more functions. So we've already seen polynomials, we've already seen rationals. 5.2 we'll see exponential, and then that's where we'll stop for exam 3. So exam 3 will be all of chapter 4, and then 5.1 and 5.2. After that, we'll get into different types of functions after that. So before we can talk about exponentials and logarithm, we have to talk about this idea of inverse functions. What does inverse mean to you, like, just in everyday language?
Like opposite.
Opposite, right? Yeah. So like we do inverse operations, it's the opposite operation. So that's exactly what it is for a function. So for a function, every function, there's always inputs that we consider the domain. We put them in the function, beeper, buffer, beep, and we figure out the y values. Those are the outputs. Those are what's in the range. So inverse functions, we're just going to be flip-flopping those both, all right? So let's read on. It says, when we go from an output of a function to its input or inputs, we get an inverse relation. So we're just going from the range to the domain. When the relationship's a function, then they'd be considered an inverse function. What does that mean? Way back when, a function was when every x had one y, right? So when we flip it, we want to make sure every y has one x, basically, in a nutshell. So it says interchange in the first and second coordinates. So interchange the first coordinate, which is usually x, with the second coordinate, which is usually y. We're going to come up with a relationship that's called an inverse relation. So here's an example. Say we have this relation, and we don't know what exactly it is. We don't know what h of x is. We don't know, like, you put it in and what operations you did. But all we know is that the ordered pairs that lie on this function is negative 8, 5, 4, negative 2, negative 7, 1, 3.8, 6.2. Notice the inverse is denoted with h to the negative 1 power, and all they did was flip-flop their x's and y's, right? So look at our first ordered pair. It was negative 8, 5. Now it's 5, negative 8. All we did was flip our x with our y's, all right? So let's do that for example 1. So example 1 says, consider the relationship G given by G equals 2, 4, negative 1, 3, negative 2, 0. Graph the relation first. So let's do that. So what we're going to do is we're going to just plot these points. 2, 4, over 2, up 4, 1, 2, 3, 4. Label that. Negative 1, 3, over 1, up 3, 1, 2, 3. And negative 2, 0. All right, there's the relation. And then it says find the inverse and graph it as well. So to denote an inverse, we use to the negative 1 superscript, all right? So G's inverse would be G to the negative 1. It's a set of points, so we're going to use squiggly brackets. And all we're going to do is flip-flop your x's and y's, right? And so instead of the point 2, 4, we'll have the point 4, 2. Instead of the point negative 1, 3, we'll have the point 3, negative 1. Instead of negative 2, 0, we'll have 0, negative 2. And we're going to take those 3 points and then plot them. So 4, 2 means you go out 4, 1, 2, 3, 4, and then up 2. 3, negative 3 means you go out 3, 1, 2, 3, and then down 1. 0, negative 2 means you stay at the origin, but then you go down 2 units. All right? So what we're going to talk about, I'll do it now, but we're going to talk about it more distinctly here in a second when we flip the page. It's not that it's a circle. That kind of does. It almost makes a hexagon, doesn't it? But I'm glad you're looking for a pattern. What it is every relation and its inverse is symmetric about the line y equals x. Okay? So the line y equals x has an x-intercept of 0, so it just goes through the origin, and it has a slope of 1, up 1 over 1. So it's just the line that goes straight through the origin, goes up 1 over 1. And symmetric about that just means if you were to fold that xy coordinate on itself across that line, you would see that this guy would fold onto him, this guy would fold onto him, and this guy would fold onto him. And we'll talk about that a little bit more specifically here in a second. So it says if a relation is defined by an equation, we're going to interchange the variables, and that produces, so switch it, x goes to y, and y goes to x. And when you do that, that is going to be your new inverse relation, okay? So I give you more room. It's just that the pictures on top of page 2 weren't going to fit on here. So I give us more room than we need, okay? It says find an equation for the inverse of this relation. So if this relation is y equals x squared minus 2x, all we're going to do is make the y an x and the x a y. So this is x equals y squared minus 2y. And you're done. There's the inverse. All right? Well, so far we're kind of just talking about relations, and relations means they're not necessarily a function, all right? So we'll talk about them and how they look, but then we're going to get into the special kind where it's actual functions. So go ahead and flip it to the top of page 2. This is kind of what I was talking about here. So if our original function was that y equals x squared minus 5x, that's just a parabola, right? So if we were to graph him, he's right here. So we'd have to use x equals negative b over 2a, find its vertex, find out that it shifted this way. So here's the original function. But how would we come up with this inverse? It's kind of awkward. But what you do is you switch every y to an x, so notice that changed to x, every x to y, so notice it changed to this. And then you do a t-chart, but instead of randomly picking your x's and plugging them in, you actually randomly pick your y's and plug them in, and you get your x's. And notice it's a parabola, but just changed on its side, all right? But again, notice that that relation and its inverse is symmetric about this line, y equals x. So that's all it's saying right there. So we'll star that because that's important. Graphs of any relation and their inverse are always reflections of each other across the line y equals x. So what have we learned so far? It says an inverse of a relation occurs when you switch the inputs x's with the outputs y's, and the graphs of the relation and its inverse will always be reflected about the line y equals x. So those are the 2 takeaway points. But again, we keep just using this generic term, relation, relation, relation. We care about functions. So let's talk about one-to-one functions. A function f is one-to-one if different inputs have different outputs. So that means if you go from x to y, your input has to go to a different output. And I'll show you what we're talking about. So we're going to do 3 little things. So on this side, we're going to plot 1 and plot 3 in our little domain. So this is where our x's are. And then we're going to plot 2, 5, 7. This is where our y's are. Whatever this relationship is, I don't know what it is, but it has 1 go to 2. So every x had 1 y, okay? But then 3 goes to 5 and 7. So can this be a one-to-one function? No, because it's not even a function. Remember, a function is every x has 1 y. And what do you notice about this relation? 3 has 2 y's, right? So this is just not a function. And if it's not a function, it definitely can't be a one-to-one function. All right, let's switch it up a bit. Let's graph 1, 3, and 5 in our domain. So these are our x's. And let's plot 2, 5. We'll leave it like that. I just do 2 and 5. I can't read my handwriting. Okay. These are our y's. 1 goes to 2, but both 3 and 5 go to 5. Is this a function, yes or no? Yes. Is it a one-to-one function, though? No. So basically a one-to-one function just means if you went backwards, do you follow the same rule, right? So every x has one y. So 1 has 2, 3 has 5, 5 has 5. So even though 5 had 2 x's going to it, that's okay. So this is a function. So we'll write function. But we'll write semicolon, not 1 to 1. And why is it not? Just flip it. Like if this was our domain, 2 would go to 1, but 5 went to 2 things, right? 1x had 2 y's, if you want to think backwards, okay? So if you go to the definition, it says, a function f is 1 to 1 if different inputs have different outputs. And notice these different inputs have the same output, all right? So up here, f of 3 equaled f of 5, and that's what we don't want, okay? So notice it says if a doesn't equal b, so 3 does not equal 5, then we don't want their y's to equal each other either, and they do, okay? So that's not 1 to 1. So let me give you an example of one that's both a function and a 1 to 1 function. So let's plot 1, 2, 3, and let's plot 3, 5, 7. And let 1 go to 3, 2 go to 5, 3 go to 7. Is that a function, yes or no? Yeah. Every x had one y. Is it a 1 to 1 function? Yeah. Yep, because every y has one x, correct? So this is a function. And then semicolon, it is 1 to 1. And hopefully the name 1 to 1 makes sense, right? Every x has one y, every y has one x. So this is 2 to 1, really, right? But here you have 1 to 1, 1 to 1, 1 to 1, all right? So I think they kind of word it more difficult than they need to. Basically, just think of a function. Every x has one y. So when you want to know if it's 1 to 1, just go backwards. Every y just has one x. And in this case, 5 had 2 x's that it went to, so it wasn't 1 to 1. Or and you can physically see it's not 1 to 1, right? It's 2 to 1. All right, so if it's a function, we know we denote it with f or g of x or h of x or whatever we want to call it. So if it's a function, we always denoted it with f. So how are we going to denote its inverse? With the -1 power, and we just say f inverse, all right? Another note you want to make a note of, because this is important because people want to start doing this and using this feature on their calculator. The -1 as the superscript is not an exponent, meaning this is not f raised to the -1 degree, meaning it's the reciprocal 1 over f of x. This is just a notation for inverse. So if you're given f and they want you to find the inverse, don't take the function and raise it to the -1 power and think that's the inverse, okay? So it's literally just a notation. All right, so we added something to our list. Let's see what's going on. It says, if a function is 1 to 1, then its inverse is a function, and that's what I was saying. If you could go from y's to x's, then that's what we have. The domain of a 1 to 1 function is the range of the inverse. So that's kind of tricky, but let's underline. So the domain of f is the range of f inverse. The domain of f is the range of f inverse, and then vice versa. The range of f is now the new domain of f inverse. Opposite, backwards. All those words are what you want to think of, right? So we'll go back up to this one. This was f's domain, x, and we went to y. This was its range. So this was the domain of f, this was the range of f. But then if we want the inverse of f, we're going to go backwards. So what are we going to start with? The y's, which is technically the range of f. So it's just, you just flip-flop them, okay? We're flip-flopping our x's and y's. We're flip-flopping our domain and ranges because our domains are made of x's. Our ranges are made of y's. So if you were kind of following that, I know that's a mouthful to take on. Let's go ahead and look at the top of page 3. We just have a lot more to take in mind. Okay, we're going to stop and summarize again. An inverse of a relation occurs when we switch our x's and y's. So every relation can have an inverse, okay? We just flip-flop the x and y's. The graph of a relation and its inverse are always reflected about the line y equals x. So you should be able to graph every relation, and you should be able to graph every relation's inverse. But there's a specific kind we care about, not just any relation, but a 1-to-1 function. And what makes it 1-to-1 is if all the outputs are different. So every x goes to one y, but every y goes to one x. And if a function's 1 to 1, that just means when we went backwards, its inverse was a function, denoted f of -1. So this hopefully kind of sounds familiar. In order, oh, I'm reading it, it's not even on this page, I'm sorry. The horizontal line test, guys, remember in order to see if a function or a graph was a function, we had the vertical line test, like every x, you only crossed it once. Well, horizontal line test now helps us with 1-to-1 functions because every y has to have one x, right? So when we draw it here, I know it's kind of faded. If you draw it here, this value of y, whatever it is, say it's like 1.2, has two x's, a and b. So since it has one y has two x's, it's not 1-to-1. Whereas this graph not only, oh, and here it's showing you, sorry. I was like, oh, I'm going to keep going. So all it's showing you is if this was a function, its inverse would look like this. And what do you know about its inverse? 1x has 2y. So its inverse is not a function, so that means that was not a 1-to-1 function. So now we have two things to look for. Is it a function? Oh, are you kind of glaring at it a little bit? So all it's just saying is that you don't even need to consider, this is the inverse, okay? It's just saying you don't even need to consider the inverse. You can just look at the original. And if the original doesn't pass the horizontal line test, that means its inverse won't pass the vertical test. Okay, that's all it's doing, because we know you're a function if you pass the vertical line test. So one way we could do it is take the function, find its inverse, see if it passes the vertical line test. Or a shortcut is, hey, the opposite of a vertical line test is a horizontal line test, so we can just look at the original function and realize this is not going to be a function, okay? So this is still a function. It's just not a 1-to-1 function because its inverse is not a function. Does that make sense? Yeah. There's a lot of inverses and function words thrown out there, okay? So it says a relation of a function if it passes a vertical line test. So a function is 1-to-1 if it passes a horizontal line test, and we'll just make note of that. So a function is 1-to-1 if it passes the horizontal line test. Okay, so all of these things, A through D, are functions. Because notice all of them pass the vertical line test. So they all are functions. The question is, are they a 1-to-1 function? Okay? So in order to be a 1-to-1 function, that means you have to pass the horizontal line test. Does A pass the horizontal line test? Yes. Yes. Every horizontal line test only goes once. So yes, 1-to-1, because it passes the horizontal line test. I'll put a check mark. It passed the horizontal line test. Check mark. All right, what about B? This is a very common function, right? This is just an x squared. Is it a 1-to-1 function? No, because almost every single x has two y's. So this is no, it's not 1-to-1. So it does not pass the horizontal line test. Big ol' X. My handwriting's kind of sloppy. All right. So this is a cube root function. Remember, the cube root function is just the inverse of the cube. So it is a function because it passes a vertical line test. The question is it a 1-to-1 function? No. It actually is. This seems like, remember, it's really close to horizontal line. It's going to have like a very slow increase, but it is increasing, right? So like you can't extend that arrow. So it is slightly going up. So a horizontal line will only pass it once. So this, yes, this is 1-to-1 because it passes the horizontal line test. Check mark. All right. And then this is just a crazy 5th degree polynomial. Why do I know it's a 5th degree? Well, first of all, it says it, but it has opposite arrow, so I know it's odd power, but there's other crap going on the inside, so I know it's not just a cubic. All right, so it is a function because it passes a vertical line test. Is it a 1-to-1 function, though? No. No, so notice here, up here, we passed that test, and down here, we passed that test, but it's every horizontal line has to cross at most once, and here we cross once, here we cross once, here we cross 3 times. So no, it's not 1-to-1. Because it does not pass the horizontal line test. Big ol' X. All right? So that's one quick way to do it. So now that we know what an inverse is, and now that we know that there's special inverses called one-to-one functions where its inverse is a function, how the heck do we find inverses? So this is a very key thing in finding inverses, guys. These are the steps we're going to use. These notes, we only do one, so I can randomly pick another function if we want and do it as well, okay? So you have a little bit more than just this one to look at. So let's look at the top of page, oh, let's read it first, sorry. So the first thing we're going to do is when you're going to be given a function and they want you to find the one-to-one function, how they give you the function is in f of x, but they want you to remember that f of x is just a fancy way of saying y, okay? So when you're given your function, the very first step is just to write y equals blah, 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 all right? Step number 2 says, well, how do we find an inverse? We flip-flop our domains with our ranges or our x with our y's. So now that you have a y written in all your x's, flip-flop all of them, okay? And then ultimately solve for y. And sometimes that can be trickier than others. So that's why I think I might just grab one randomly and do it with you just to make sure you feel comfortable. Once you solve for that new y, rewrite it as a function of f, but state that it's its inverse. So we'll use f to the negative 1 power, all right? So let's go ahead and do this. I'll leave, can I do that? Can I somehow get there? Okay. So here's our steps in the upper right corner here, okay? So we want to find the function 2x minus 3. First, we have to decide, is it one-to-one, okay? So how do we know if it's one-to-one? I'm graphing that bad boy, and as long as it passes the horizontal line test, I know I'm good to go. Well, what is that graph going to be? 2x minus 3. That's just a what? A line. So isn't every line going to pass a horizontal line test other than a horizontal line? Yeah, but let's just, graph it for practice, okay? So our y-intercept's at negative 3, 1, 2, 3. And our slope is 2, but think of it as 2 over 1. So we're going to go up 2 to the right 1, up 2 to the right 1. So we'll go up 2 to the right 1, up 2 to the right 1, up 2 to the right 1. So as best as you can, kind of follow that pattern throughout the coordinates. I need to bring a ruler. I like to be exact, and mine's not very exact, okay? So this is our function f of x. So is it one-to-one? So I'll just make that a bullet. Is f of x one-to-one? We're going to put it yes, right? Why? Because it passes a horizontal line test. Do you guys agree? So horizontal line test says if you pass the horizontal line test, then you're a one-to-one function. So we got that question. Then part 2 or whatever it says, if it is one-to-one, let's find a formula for f inverse. So let's make a bullet point for that. But we're going to use, where did they go? These 4 steps, okay? So in this bullet point, I'm going to do these 4 steps. Step number 1 says take your function f of x and replace the f of x with y. So I'm going to take f of x equals 2x minus 3, and I'm going to rewrite it as y equals 2x minus 3. That's how we knew to plot the graph, right? Step number 2 says now that you have it in terms of x and y, what is an inverse? Everything's flip-flopped, all right? So in step number 2, we're going to flip-flop our x with our y and vice versa. So this is x equals 2y minus 3. Is that okay so far? And then step number 3 says solve for y. So we want to get y by itself, right? So what's the first move we're going to make? Add 3 over. So we'll have x plus 3 equals 2y. Is that okay if you kind of can just see it visually without showing the movement, right? If we add 3 on the right, the negative 3 and the positive 3 will cancel. If we add 3 to the left, x and 3 are not like terms, so it just stays x plus 3. All right, last move, what are we going to do? We're going to divide both sides by 2. So y equals what? X plus 3 all over 2. So what is our inverse that they want us to do? Well, step 4 just says instead of y, use the notation for a function, but let us know that it's the function's inverse. So this is f of negative 1, or f to the negative 1, or f inverse, equals x plus 3 over 2. I'm going to go a step further and write equals. why? You can put it like that. MyMathLab actually will accept x plus 3 over 2. But I want to write it in slope-intercept form so that I know how to graph it, okay? So anytime you have x plus 3 divided by a constant, it means you just have to divide both parts by that constant. So what is x's current coefficient? 1. So when I divide by 2, it's just 1/2 x. Do you agree? And what do you get when you divide 3 by 2? You just get 3/2. So MyMathLab will take either or for the inverse. That's ultimately what the question's asking, so let's box it in. They'll take either one. So if you want to, if it's easier to just type the fraction bar once and put x plus 3 over 2, that's fine. But the reason why I go the extra step is look at the last thing we're supposed to do, compare the graphs of each on the same graph, right? I don't know how to plot this line when it's in this form, but I now know how to plot this line, okay? So 1/2 x plus 3/2, what's my y-intercept? 3/2, but what is 3/2? 1.5, okay? So I'm going to go up to 1.5. There he is. And then what is his slope? 1/2. So that means I'm going to go up 1 over 2. But just be careful, because since we're sitting in the middle of a box, when we go up 1, we'll be in the middle of a box, all right? So when I go up from 1 here, I'm going to be halfway here, and then I go over 2. 1, 2. And then when I go up 1 from here, I'll be halfway here, but I got to go over 2. When I go 1 here, I'm going to go over 2. So you get this general line going, and we can label it f inverse of x. And what do you notice about the two graphs? They are reflected about the line y equals x. So no matter what, if you do it and you're like, oh my goodness, I don't know if I did it right, you can always throw each of them into your graphing calculator. And if they look symmetric, and sometimes I hit the zoom, I forget what number it is, zoom square, so it makes my graphing window square, not rectangular. You see the symmetry a little bit better there.